So great. So welcome back, everyone. So sorry. So I had a few difficulties connecting. So there's some sort of software update I probably have to do, and so I'm not connecting the way I'm usually supposed to be doing. So let's look at the schedule. So quickly, close this. Hold on. So let's see. So we had the quiz one. I will talk about quiz one in just a minute. It should be either all graded now or might be a few adjustments. So coming in just today. But it should be mostly graded. So homework one is due at the end of the day today. There have been, if you haven't seen on the discussion board for Canvas, there's a lot of good discussion on the discussion board. So there are lots of questions that people have posted that probably a lot of people have, and the TAs, myself, have been helping provide some guidance. So in fact, people are getting slightly confused at the exact spots we expected people to get confused. This is good. This means you have to think deeper about the examples we went into class, which is the point of the homework. So great, but it seems like people are making progress towards the solutions. You should keep in mind, homeworks are worth 60% of the grade in the course, so make sure you do well in the homework. If you have questions, the discussion board has been a good place. A lot of people recently in the office hours for the TAs. I'll be available after class. Anna should be available after she has office hours on, today, 12:30 to 2:30 as well. It's a smaller room, so, she will do what she can. But we've had a bunch of other office hours. That's why they're there. And then homework 2 will be posted by Thursday. The other thing to see in the schedule is that we are in the last section of the convergence part. The first 2 sections, probably review, Bayes rule, and the convergence are going to be the main parts that focus on the probabilistic aspects of data analysis in this course. They're mostly there to provide a foundation. There'll be a couple times we'll talk about expected value and various things in the course. We derive this sum of squares, this cost function for estimating the mean. That was the sum of the squared distances from the point. You want to minimize that. That will show up a whole bunch of times the rest of the course, but we won't necessarily derive through all the probability again. We probably won't, in fact. We'll just use that as a starting point. In this section, in the convergence, we're kind of explaining probabilistically why as you get more and more data, it's going to help your estimate get better. And so in the rest of the semester, we'll be seeing, okay, what happens when we get more and more data? We should get a better estimate. And this is explaining why that has happened, right? But it won't be as much probabilistic view after this lecture. So if you haven't finished a probability course before, it's been a long time, and this part of it has been a little challenging, we'll kind of shift gears, and it'll be more algorithmic, maybe kind of more linear algebra perspective, in fact. So just kind of, if this section of the course went a little was more challenging, we're going to switch gears a little bit, but it will kind of influence the core ideas of it will influence kind of a lot of things we'll be doing the rest of the time. Okay. All right, so let's get into the lecture. Yeah, so we'll talk about, convergence and concentration of measure. Again, these are going to be kind of simple techniques to understand how to kind of get a bound on what happens when you get some more and more data, how to do some calculations that are not too painful, right? These calculations can be quite complicated. If you look in statistics sort of literature, there's a lot of very fancy things you can do. I'm going to give you kind of the bare bones mechanisms to see how this works and to kind of get the main ideas. I want to say a little bit about quiz 1. Okay, so I want to say kind of 2 statistics from the quiz. These might be slightly updated, but the average score was so the average score was 89%, and the average time was 25 minutes. So I think we calibrated the quiz not right. It was slightly too hard. I expect the average score over the entire semester, after you've taken all the quizzes, to be closer to between 90 and 95%, 92, 93%. I expect the average class score for the quiz to be there. So expect the other quizzes to kind of, I expect you to score better on them. Okay, so some of that will be us changing the quizzes, right? So there's not as hard questions. Some of you, I think you will do a little bit better in preparing for them. If we're gonna have a quiz that's too hard, I guess I'd rather have it at the beginning of the semester and then you work harder the rest of the semester than it happening at the end and you all being surprised and kind of unexpected. So, one thing you could do is I glanced at some of the the cheat sheets that you turned in, so I think some of those you could have spent a bit more time on those than you actually did. I know it's open book and you can use the other resources, but if you haven't gone through all this stuff yet, it's harder to do that during the quiz. So that's kind of the point of those. Yeah, and there was one question on there where we basically were asking you to apply the rule that if you have a random variable x and you have some equation, so you defined a new random variable, and there were different forms of this, but it basically had something like, well, alpha times x plus c, where these guys are constant, scalars, right? And then you were asked both the expected value of this, right? The linearity of expectation. We hope that you would know that the linearity of expectation, you can do alpha of x plus c, right? So this one, I think it was a fair question to ask. The other property that I was a little bit rushed in the lecture, and I forgot to cover this in class, where this should be alpha squared times the variance of x, and the c is something that just it is disappearing. Okay, this formula, it's in the book. I thought I covered it in class. I realized I did not cover it in class. So this was worth 10 points. We gave everyone a fudge factor of 10 points on their quiz. So if you got it right, you could get get points. You earned extra points. No one went over 100. But if you didn't get this wrong, well, you didn't lose points for this. All right. So there were a couple of other minor things, and we're trying to correct and be liberal, and we're giving a couple of partial credits, and that might be going in now. Yeah. Yep. Yeah. So right, there was also a question with Bayes' rule where the probability, if you calculate, was equal to 2. We gave people full credit if they did that, or a couple of people commented on this and pointed this out. That's great that is not possible. We try to be careful about this. If you think you lost points because of this, you can so you can contact us. But we tried. There were a couple of issues with this first quiz, and we will do better on the next quiz. But all right. So we've tried to correct for these factors as well. Okay. It was also probably a bit longer than I wanted. Probably the more challenging takes you longer. The 25 minutes. Again, I expected 25 minutes. My goal is for this to be in the 15 to 20 minute range. Okay, so I expect the quizzes again should take you less time. These two things are correlated. If the score is lower, probably it took you longer because you're trying to figure out something you didn't know ahead of time, or it was too tricky. So that's the first quiz. You know, I know there's a lot of other. I don't mean for this to be a statement on any particular person in the class. There are various things we can talk about if there are challenges, but we will be moving forward into kind of some newer directions. And I think the future quizzes, you will be able to score some better on the future quizzes. I think there'll be a combination of kind of both you guys preparing better and me kind of preparing quizzes which are more representative of what I'm after. Okay. So great. So let's get on with the lecture here. Okay, so we talked about the central. My wires all in a bunch here. Okay. Last time we talked about the central. So the central limit theorem. All right, and so this was if I have n IID, so random variables, x1 up to xn, and I consider the average 1 over n. Xi, I want to say that the average is actually a good estimation of what's going on here. I can point out that the expected value of the average is equal to the expected value of each of these random variables, right? So x bar is also a random variable, but it's going to be more concentrated. And I can say that the variance of x bar is going to be equal to the variance of each of these xi's divided by n, right? So the variance is going down by n. In fact, this is a fairly straightforward consequence of the property I said about how variance is affected by multiplying by a scalar, or if I add two random variables together, you add up, these. So if you look at x bar, it's dividing by 1 over n. The 1 over n factors out as 1 over n squared, but I'm adding together n things. So I factor out an n and a 1 over n squared, right? And so I get 1 over n is left over here. Okay, so so the variance is going down, right? So as I have original distribution, this is for the distribution of f of x, and then I'm going to have a concentrated distribution f of x bar. Okay, so they're going to have the same mean, right? But the variance is decreasing. It's becoming more concentrated, right? And remember, these distributions, they're probability distributions. They integrate to 1, but the values can be much larger than 1 at any point, right? As long as the integral is 1 here. Okay, and then the third factor here is that x bar looks so normal. Okay, as in it's actually approaches a normal distribution. Okay, and we're going to talk. This is harder to quantify, and we're going to look at a very kind of blunt, but actually very useful ways of quantifying this that'll allow us to say how well we're actually doing when we're looking at a lot of data. Have we gotten enough data to concentrate kind of so well enough to get a good estimate of what's going on? Okay. Okay. Then at the very end, I mentioned these probably approximately so correct view of this, right? And this is the view of that we're going to take to try and bound how accurate. This is going to be how accurate is X bar. Okay, so I want to try and answer this question of how accurate is X bar. And this is kind of, it's a little tricky to do. And these probably approximate correct, which is, so it's, so kind of it's so kind of a mouthful to say. And the form is also a little bit complicated, especially the first times you see it. So we're going to say we want that X bar, we want that it to look like the expected value of Xi, the random variables, or I can just write this as, you know, this is kind of a general form. It can take, there are variations on this. Okay, but I want it to be close to its expected value. Okay, so I want a random variable which is describing either my analysis process or an algorithm that I'm running, right? Randomized algorithm, and I want that to be close to its expected value. And so what do I mean by close? So I'm going to look at the distance, just the absolute value of the difference. It could be too high, it could be too low, but I just want to say it's close. And I'm going to say the probability, and I will say it's not close if it's greater than some parameter, so epsilon here. And I need to wrap this in a probability because it's a probabilistic notion. So I want to say, well, it's a random variable, so I have to say that it's not always going to be less than epsilon error, but it's going to sometimes be less than error, and I want that the probability it's more than epsilon error to be small. Okay, so this term, this is an error, so tolerance, okay, and this guy is a this is a this guy is a probability of so failure. Okay, so the probability that I fail in my goal, that I have too much error. Okay, so if I have, let's say, a distribution, this is the expected value of X bar. Okay, and I've got some distribution, and it can look like anything. Okay, it's if we're using, you know, if we're using an average, it's going to look like a normal distribution, but it could be anything here. And then I'm going to have some error tolerance. So this distance would be epsilon. Okay, and anything, if my random variable, right? So this is the, say, PDF of X bar here. Right? If my random variable falls in this range, everything I say is good. That's within my error tolerance, but there's some probability of failure that it falls outside this range. Right? So the sum of these two terms is delta. This is the probability it falls outside my range, which I say is okay. Okay, so when you're dealing with random variables, you can't just say, okay, did I achieve my goal or not? Or what's the probability I got the exact right answer? But you can say, what's the probability I'm close to the right answer? And so that's what these kind of, any sort of randomized analysis looks so like this. Well, this is a kind of, this is the most common form. This is the Monte Carlo form. So Las Vegas form sometimes, but we're not going to worry about that. Okay. So this is the most common way of kind of assessing how well does a random process work, or how that could be a random analysis process, or do we have enough data, and that's a probabilistic statement, or is it a randomized algorithm? Okay, so we want to get this, and as this data approaches the normal distribution, and if the variance is decreasing, we should be able to say we get more data. These tails, the probability of failure is decreasing. And in fact, it's decreasing for also smaller and smaller values of epsilon. So we're getting closer and closer to our estimate, right? So we want to figure out how to quantify this, right? I kind of said in practice, but not how we fully can quantify these sort of bounds. And that's what the rest of this lecture is going to be about. Okay. Okay. So I'm going to give this lecture. We're going to give 3 different tools in order to do this, and they're going to become slightly more complicated but more powerful as we go. Okay. This first one is the Markov inequality, and this is for a random variable x. Okay, and I'm going to bound this. I'm going to write down something that looks like this pack bound for this random variable x. And in order to apply these bounds, I need to know certain types of information. In the Markov inequality, I need to know the expected value of x. I'm going to compare to the expected value. So I'll always need to know what is the expected value, because that's what I'm really after here. And I'm also going to need to know that x is greater or equal to 0. Okay, these are 2 things, properties I need to have in order to apply this. Okay, if I can have these, I can say that the probability that x is greater than some parameter alpha is less than equal to alpha divided by the expected value. Okay, this is, if I have these properties, the expected value is known, and I know the random variable is always greater than 0, I can say this property for any, for any alpha greater than 0. Okay, if I set alpha less than the expected value, this is not necessarily going to be very meaningful. But I want to set this to be typically larger than the expected value. What? Yeah. Yes, great. Thank you. I knew something was off there. Expected value of x divided by alpha. Great. So thanks, right? And so as we get, if we set, great. That's why if we set alpha less than the expected value, this will be a probability which is going to be going to be greater than 1, and that doesn't tell us anything. It's not wrong. It's saying if the probability is less than 2, well, I know it's a probability, as you pointed on the quiz, the probability has to be less than 1, right? Any probability has to be less than 1, but as alpha gets larger, this becomes sort of more interesting. Kind of the way to see why this is true is if I have kind of so I have to, this is 0, and I have a probability distribution here, and I know the expected value of x is here. Okay, and all I know is the expected value is x. Well, I don't know what the probability distribution is. It could be here, but in the worst case, if I wanted to say that there was some value of alpha out here, and I said, what's the probability that, say, 5%, 0.05 of the mass is out here at this alpha? Well, I need to know that with the expected value, I have to have a probability distribution on your hand. It's kind of like if you're a waiter or waitress balancing a tray of drinks. The expected value is the center of mass of the distribution. Okay, and so it has to balance under your hand. Where your hand is has to be the center of mass distribution. Otherwise, it's gonna fall over. Okay, and so the expected, if I know the expected value and I know some part of the mass, say 5% is very far out, well then the rest of it, you know, it's greater than 0, so the rest of it has to be piled, right here, basically at 0. It can't be further left than 0, but the expected value needs to somehow be in that same spot. Okay, so as I push more and more mass, if I push mass further out, right, alpha is larger, then the probability that it's larger than that threshold has to go down because it has to balance. Okay, and so that's kind of where this Markov inequality is so coming from, right? I can write the expected value of x. Okay, I can write this is equal to so the probability that x is equal to 0, right? So if I push some part of it equals to 0, right? So there's some part equal to 0 in the worst case, and plus the probability that x is equal to some alpha, right? So either I consider, if I wanted to be greater than alpha, let's not push it too far. Let's say it's exactly alpha or it's 0. This is the kind of the most extreme case. And if I take the expected value, well, kind of this term is going to be worth alpha and this is going to be worth 0, right? So the expected value of a continuous or discrete probability distribution I can write down this way: 0 times the probability it takes the value 0 plus alpha times the probability takes the value alpha. Okay. The first term is 0, right? So if I set this to be this term to be delta, then this term can be 1 minus delta, right? But this first term completely goes away, and I have alpha delta, right, which is left because I'm multiplying by 0. And now if I solve for the probability of failure, I set this equals to delta, right? That's the probability of failure in the in the pack bound. Then I can get that the expected value divided by alpha is equal to delta here. Okay, and this is kind of the most extreme case. And then you can reason every other case must have a bound which is not as extreme as this. But this is where you get this probability of failure is equal to expected value of x divided by alpha. Okay, so there's a little bit of algebra here, kind of based on this balancing of a trait example. Yeah.
So are you multiplying that first part by 0 as part of like a proof or something?
Yeah. So you know, this is not a full proof here. I haven't quite reasoned out all the corner cases, but I'm trying to argue that the extreme case of the expected value being here, if I want to have how much mass can I have at a value of alpha? Well, I'm going to put it exactly at alpha, not bigger. And I'm going to say set this probability of this mass to be delta. That's, say, 5% in the example up there. And then that means that if I want the expected value to stay the same, I can maximize the value of delta by putting the rest of the mass exactly at 0, right? And this is the equation for the expected value. This first term becomes completely 0 because I'm multiplying by 0. And the second term is alpha times delta. And if I solve then for delta, I get expected value of x divided by alpha. Okay, and this is basically where this Markov inequality comes from. So it's a truth about random variables that are greater than 0. So I can get this bound. And so this kind of looks like a pack bound. What I actually might do, I can write this as the probability of x minus expected value of x is greater than epsilon is less than or equal to expected value of x divided by alpha minus expected value of x. So it's right. So I did some algebra where I set alpha equals to right, let's say I set epsilon equals to alpha minus expected value of x. Okay, and then this one looks like the pack bound I wrote on the other page. but this is the most common. This here is the most common form. Okay. All right. So this is the main bound here. Okay. Okay, so this kind of tells me some sense, if I just know the expected value and that it's not greater than 0, that I can say, okay, I can't be too far on the tail. The probability of something being too large is bounded. Okay, so this one is kind of a weaker form, but I didn't need to know very much information. I just needed to know the expected value and it's greater than 0. There's a stronger form of this, and this one will maybe, here, actually, let me go through a simple example, and then well, actually, let's do this after the, so the next one, and we'll do them both together. Okay, so the Shebishev inequality, okay, is another inequality you can apply. And this is, again, for a random variable x. Now I need to know the expected value of x, and I need to know the variance of x. I do not need to know if it's greater than 0 or not. The variance kind of gives me a bound on the spread in both directions here. If I knew the standard deviation, I also know the variance, right? So those are equivalent to each other. Okay, and this gives me a different bound I can apply. The probability of x minus expected value of x is greater or equal than epsilon, right? This is our pack bound. But now we can write this as a function of the variance. This is the variance of x divided by epsilon squared. This is my delta. Okay, so this is the Chebyshev inequality here. Okay, so what is this saying is that as the variance gets smaller, so does my upper bound on the probability something is larger than epsilon, right? So now I have the expected value of x, and I have something like the standard deviation, right, which is the square root of the variance, right? Or so maybe I can write this as actually square root of the var of x, right? Okay, and so if I have a distribution, okay, and I know the expected value and the variance, then I can look at some probability of some tail being, so this is epsilon plus the expected value. Okay, it also bounds, it's two-sided, so this one also, this would be epsilon x minus epsilon. It also bounds the probability of it being too small. It's bounding both directions. Okay, so this, and if the variance were to shrink, right, then the probability of it being out here is going to be smaller, right? The variance shrinks, it has to integrate to 1. That means there's more concentrated here. It means there's less room in the tails. Okay, and this should look a lot like the, this is kind of a direct instantiation of the, oh yeah, we'll see it with the central limit theorem in a second, actually. Okay, so let me go through an example of applying these. Okay, so let's say I have a random variable r, which is the rain in SLC in June. Okay, so rainfall, you know, I know it's dry in Salt Lake City, but the rainfall has to be positive. Okay, so I know that r is greater than 0. I can look up, and it turns out the expected value of the rainfall in June is about 20 millimeters. This year it was so like 11 millimeters in June. Okay, and I want to know, say, what's the, and so if I have this information, I can apply, which inequality can I apply now? The Markov inequality. I can't yet apply Chebyshev. I need the variance or standard deviation here. Okay, and so I want to understand the probability that it's going to rain more than 50 millimeters. so in the next June, what's the probability it's going to rain more than 15 millimeters? Things like rainfall and temperature used to be great examples of random variables because there's historical data you can get something like an average on. Now with global warming, I don't know if these still are very good examples, but ignore that. Or maybe it's not good to ignore it, but you know, for the purpose of this example, we can ignore it. Okay, so the probability that the rainfall is greater than 50 millimeters. Okay, and so we're going to say that using the Markov inequality, I can say this is less than the expected value of R divided by 50. So this would be 20 millimeters divided by 50 millimeters, right? So those cancel, the millimeters right here cancel, which is great. That's a good sign. And that's 0.4. So 40%, the Markov inequality tells me 40% probability that no more than 40% probability that the rainfall is greater than 50 millimeters in an average June. Okay. Okay. So this is an example of the Markov inequality in action. Yeah.
As you mentioned with the error markings, it could be greater than, could it also be less than? Like if we have a range of like, it can only be from this
yes.
to this.
This is an upper bound on the probability. As we'll see, we're going to get another upper bound on the probability, and this one is going to give us a smaller upper bound. That will be better, right? It can't be larger than 40% of the time. So global warming, assuming my probability, my expected value is true, if I were to run, you know, an unbounded number of simulations of June in Salt Lake City, the no more than 40% of the time is it going to have more than 50 millimeters of rain. That's what this is saying.
Is this also like contingent on the fact that you don't have infinite variance?
Yeah, if I have variance, we'll see next. If I have found on the variance. Oh, yeah. No, this is not contingent. I did not use that. I did not need to use that. The variance was not infinite in this case. Yeah, that's a good question. But I mean, the proof of, I mean, I just was, you know, if you read in the book, it basically explains this in a little bit more detail. It does not use anything about the distribution being bounded. That is required in the central limit theorem. That's required so that I can state something about the variance, right? That the variance is actually a quantity I can measure, and that this looks like normal. It needs to start someplace and converge, and if it's not starting someplace reasonable, then it won't ever converge. Okay, that's a good question, but that didn't come up in Markov. It does come up in the Chebyshev. This is the Markov. Okay, so now let's say, right, I also have a bound on the variance of R. Okay, and let's say, in this example, I'm going to say that the variance of R is going to be equal to 9, and that should be millimeters squared. Okay. Okay, so that's a squared quantity, remember? All right, and so now I can say, well, I have a slightly different thing. I'd like to say the probability that the rainfall is greater than 50. Okay, but there are other versions of the Chebyshev bound that are only one-sided, but in this class, we're only gonna, there are lots of variations on these. We're only gonna use the ones in the book to keep your life simple. And so I'm gonna reduce this to the one I know, and it's gonna be sloppy. I'm gonna lose one side of it. It's gonna be wasteful, but this is going to be less or equal to the probability that R minus expected value of R, that this difference is greater than 30 millimeters. Okay, remember the expected value of R was 20, right? So I subtracted 20 from both sides, and then I took an absolute value. Okay, so the absolute value kind of, it's saying I'm bounding both tails, but I really only cared about one tail. So if I can get a bound on, so this is larger. This is the counting the probability of both of the tails, and this is only counting the probability of one of the tails. But I'm doing a change of variable kind of trick sort of here. Okay, but this is the form that I can directly apply the Shebishev inequality. Okay, and that's going to allow me to say that this is bounded by the variance of R, right, divided by, this is now divided by 30, right, 30 millimeters. And this is squared. Okay, so, and this is equal to, remember, 9 millimeters squared over 900 millimeters squared. The millimeter squared canceled, which is good, and this is equal to 1 out of 100. Okay, so if I have this additional variance information, that in this case, this data, the variance, I don't actually know if that's true, but in this case, it's pretty small. If I have the additional information on the variance, that then I can say, well, the probability I exceed that variance by 30 millimeters is at most 1 out of 100. So I can get a significantly stronger bound. Instead of a 40% bound, I can get a I can get a 1% bound, 1% probability that I exceed this. Yeah.
I missed you describing where the 30 came from. It just shows a number.
Okay. No, the 30 comes from, I did minus the expected value of R and minus the expected value of R on both sides of this inequality here. All right, so I subtracted expected value of R on both sides, and then I took the expected, so I did 2 steps here. All right, so this is equal to the probability of R minus expected value of R. Other way. Of 50 millimeters minus expected value of R. Right? So this is an equality, and then I have an inequality where I've added the absolute values. Yeah. Okay, great. And then, and then I did this because then I can apply the bound. I have these equations. I'm going to reduce to those equations, and then I can apply the magic. You won't need to prove them in this class, but I want you to you'll do some examples where you actually use them in the homework. Yeah.
So we have these 2 different methods that we're using, and we get 2 different numbers.
Yep.
What do the probabilities actually mean? I could easily misread it as they're saying the same thing. They're probably
Right.
not.
They're basically bounding my goal of this. Okay. The goal here is the same. Probability that the rainfall is greater than 50 millimeters. Probably the rainfall is greater than 50 millimeters. I want to get an upper bound on this. And I have 2 ways of doing that. And they give 2 different bounds. They're both upper bounds. They're both correct. One of them is more useful than the other one. Right? I want to upper bound the probability that the rainfall is greater than 50 millimeters. The first one says it could happen 40%. It might happen 40% of the time. That's all I can say. Not more than 40%. The second one says, this is not going to happen more than 1% of the time. It's it's like a 100-year event, right? Every 100 years, this might happen. This says, maybe 2 out of 5 years it happened. That's all I can say, right? They're using different information and they're getting different bounds because of it. This one has a little bit more useful information, and so it's getting a better bound. But I don't always know which one will give a bound which is better, right? If we're talking about something much further from 0, then the Markov inequality might actually be better. Okay, so you kind of need to always apply them both and see which one is better. At some point, you kind of get an intuition of which ones to apply. Okay, but they're both bounds, and we're going to see one more bound too. That's going to be stronger, but a little bit harder to apply, right?
Another question.
Oh, on Zoom, great. Yeah, I don't have my, is a lower bound the, so the one that's better. Yeah, the lower bound is better. You want to get a smaller upper bound, right? So you have you want the probability of R greater than 50 millimeters today. This is, I say it's less than the min of 0.4 and 0.01. Okay, it's less than both of these, so it has to be less than the min. And so you want to, whichever one is the min is the one that's better. Yeah. So, but I didn't know ahead of time which one is going to be better, so I can apply them both. Okay. I want to do, there's one other cool thing with how this interacts with, the central limit theorem. So let's say now that I have x bar, is equal to 1 over n, xi equals of x1 up to of xi. Okay, and I know that the variance of xi, each of these xi's is sigma squared, has some value sigma squared. Okay, what do I know about the variance of x bar? I know from the, yeah. Variance over n. Yeah, so the variance goes down by a factor of n as the number of random variables go up. If these are, this is true even if they're not kind of, if they're independent random variables. Yeah, these are IID random variables. I know that the variance goes down by a factor n based on the central limit theorem. Okay. Yeah, these are IID. Okay. Okay. So now I can apply the Shebishev inequality on x bar instead of, or let me just say for x bar, instead of just each of the xi's, right? So the probability that this is greater or equal to epsilon, right, is going to be equal to the variance of x bar divided by epsilon squared, which is going to be sigma squared over epsilon squared divided by n. Okay? So what's happening here is, and this is the delta in my pack bound here, that as I get more and more of these random variables averaged altogether here, my pack bound is getting better, right? Remember, I wanted to get an upper bound on the probability of failure, and that probability of failure is decreasing linearly with n. As I get more and more data points into my average, my probability of failure is going down, so decreasing here. Okay, so if I have, and so a different way of looking at this is I can solve for n. So solve for n. So let's say I've got an error, my error, so tolerance, right? So I want to create an estimate, x bar, estimating my average. So let's say we're measuring heights of people at the university, right? And I want to say I want to be within 1 inch of the right height, and I'm going to have some probability of failure, and I know, and I have a bound on the expected value, or I want to estimate the expected value, but I have a bound on the on the variance. so I know kind of the variance of an average college age student is, let's say I have this information. Well, then I can solve for n, and then I can say as long as if I set n equal to basically sigma squared divided by epsilon squared divided by delta, right? If I set n equals to this bound, then I will be within my error tolerance with probability at least 1 minus delta, or the probability with probably at most delta, I will have no more than epsilon error if I can set n to this value. So this is how many data points I need to collect to satisfy these error tolerance and this probability of failure. Okay, so this kind of informs you how much data should you collect, right, to get how accurate of an estimate, right? So if you see like these polls, right, they're trying to poll for like the election, they kind of want to get within some error tolerance. You'll see these error tolerance like, plus or minus 3%, and there's probably implicitly maybe a 5% probability of failure. And if you write this down, you'll get something like 300 to 1,000 people you have to poll. Depends on some other stuff, the distribution of people they poll and so forth. But that's why the polls you see are around 300 to 1,000 people, because you can apply some sort of an analysis like this to say that gets you some error tolerance on the poll, and some probability that your error, you exceed the tolerance for error you have. Okay. So this is the central limit theorem plus the Shebishev inequality. Okay, before we do an example of this, we're going to do another error bound that allows you to get an equation like this that's better than the one you get here. Okay, my video's disappeared for better or worse. Okay. Okay, so we have one more bound that we want to cover here. Okay, and this is the Chernoff, Hoeffding bound. Okay, and what I'm writing here is not like the standard form of this. The standard form of this is more complicated. This is the bound that will give you pretty much what you need generally. It gives you a pack bound, and it will be fairly easy to use. So if you look up in resources, so like other than my book, you might find some more complicated versions of this, but this is kind of a simplified version, and so you can thank me for giving you the simplified version. But this is almost always so the version which is needed here. Okay, so we're gonna have random variables, x1, x2, up to xn, and these are IID, and so we're gonna know from some, underlying sort of distribution here. Okay, so this one is specifically applying to this latter case of the Chebyshev inequality. This one you apply with multiple random variables here. And this quantity n, right, the number of these random variables is going to be important, right? And so what do I need to know to apply this one? First, I need to know the expected value of each of the xi's. They're IIDs, so they have the same expected value. And then second, I need to know that each xi falls in some range A, B, and that B minus A is equal to some quantity, so delta. This is an uppercase, so delta. Okay, so there's some bounded range on the random variables. The Markov inequality, kind of, you could work with that if you only have one side on the bound. If you have only one side A, and you didn't have upper bound B, you can with some change of variables, you can apply Markov inequality, but here we have both bounds. Okay, this implicitly also gives a bound on the standard deviation, but this will be more powerful. You can show any distribution within some bound. You can bound the standard deviation. So this is telling me more information. That's like the normal distribution has no bound like this. It does not have a bound on the random variables. They could be infinitely big. It's just very unlikely. I cannot apply this inequality. All right, so this is more restrictive. Okay. Okay, so now I'm going to pick some epsilon greater than 0, and I'm going to write down the bound. Again, the probability that our x bar, again, we have x bar equals 1 over n of these xi's. The probability that the x bar minus the expected value of x bar, which is the same as the expected value of each of the xi's, probably that's greater than our parameter epsilon, is less than 2 x. If you remember, x of z is equal to e to the power z, right? So x of negative 2 epsilon squared n divided by so delta squared. Okay, so this is slightly more complicated form. Okay, it is, if you kind of knew the expected value, the variance, these are called, so the moments of the distribution, and as well as those are the first and the second moment. If you had the third, the fourth, and you had all the moments, you can also get a bound like this. But ultimately, what you want are the bounds on the just the upper and lower bounds is pretty easy to work with, right? This delta, the spread on them. Okay. Yeah.
Clarify the exponential. You defined the exponential function above it. That's
Yeah.
Z equals e to the z.
Right. This is it's not a shorthand, it's a longhand for writing e to the power z. If I were to write all of this inside of an exponential, it would look very crowded. Usually the font is smaller, and so I write exp, that's e to the power, what's inside these parentheses. Yeah, to be clear. Yeah. That's 2. That's a 2. Yeah. Yeah, the 2 is a constant. It's not too important. You kind of want the asymptotic properties here. The other ones didn't have these constants. If there are versions that are one-sided, it's almost the same as dropping the 2, but it's not quite the same. This comment, I don't have my help today. Is it important to distinguish between greater than and greater than or equal? So these are typically applied with continuous random variables, and then the greater than or greater than equal are basically the same. The difference is measure 0. So it's this sort of, if this was a less than instead of a less than equal, it's basically the same. Okay, so this is a bit more powerful. But before we go through an example, I can say I can set this equal to delta, and then I can solve again for n, right? So solve for n, right? Okay, great. So Anna is online. Great. Okay, so if I solve for n, now I'm going to get a different bound here. It's going to be delta squared in the numerator divided by 2 epsilon squared. Right? This part looks fairly familiar. Before I had sigma squared, which is a kind of a notion of the deviation from the mean over 1 over epsilon squared. So that's about the same. But the real advantage here is then I get a natural log of 2 over delta. Okay, so what's happened is the probability of the failure goes inside of a log term, which means that the dependence on the probability of failure is exponentially better. The way to think about this is every additional example I get I'm going to decrease, I'm going to increase decrease the probability of failure by like a bit of precision, roughly by a bit of precision, right? So if I were to write this, you know, if I'm thinking of like the digits, roughly every 3 examples, I go from 10% probability of failure to 1% probability of failure. 3 more examples, I get to 1/10 of 1% probability of failure. 3 more examples, that's 12 examples, I go down to 1/100% probability of failure, right? So it really decreases probability of failure exponentially quickly. Okay, but this 1/epsilon², this is kind of inherent. Yeah.
Am I missing something because it's in base 2 in the equation
This is not base 2, this is base E, right? So I'm actually, yeah, so this is E, it's 2 times exponential. That's not, yeah, exponential is always base E. That's what it stands for, right? That's a base E, the 2.71. This is 2.71 and so forth, right? Okay, yeah, the base E is what shows up in the normal distribution and in the Laplace distribution in this Chernoff-Hoeffding bound, and that's why you get the natural log here. Yeah, so it kind of shows up in these kind of neat sort of places. Yeah.
For probability of failure, what does that equal to in that first equation?
So delta. I'm always going to use a delta for the probability of failure, and so then this delta shows up down here.
But in this equation, you have it equals delta there.
Yeah, so that's equal to this whole expression here. Yeah, great. Equals delta. Great. Yeah. So I didn't want to squeeze it off to the side there. Okay. Right. So again, this is a pack bound. The probability that the random variable deviates from the mean more than epsilon is less than delta. Right. And this is the expression for delta. This is typically how we'll write it. Okay. If you're like a statistician, you might actually leave it in this form. As a computer scientist, we like to solve for n. How many samples do I need? That tells me the algorithm collect this many samples. And I'm given parameters epsilon, lowercase delta, and maybe uppercase delta. Maybe this is part of the problem description. How many samples do I need? Okay. Okay, let's go. Great. So good, we have some time to do some examples here. Okay, so let's start. I'm going to roll. I'm going to have a die, right? So this is going to be the rolls, 1 through 6, right? And I'm going to do n equals 120 of these rolls of this die. Okay, and I'm going to record the t is going to be a random variable, or ti is going to be 1 if a 3 and 0 so otherwise, right? And so I'm going to look at an uppercase t here. This is not the average. This is going to be a random variable for the number of 3s. Okay, so the expected value here is going to be, for a fair die out of 120 rolls, should be 1/6 times 120, which should be 20, if I did this right. Okay, so the expected value is 20. Okay, and I want to consider the probability that I get more than 43s. The probability that, we'll say that t is greater than 40. Okay, that I roll more than 43. So what's can I get an upper bound on this sort of probability? This is simple enough. You could probably compute it explicitly, but we're just going to apply this hammer of a Chernoff-Hoeffding bound to get an upper bound on this. Okay, and so the first thing we're going to do is we're going to convert it into the form that we will use in this class. Okay, so we're going to look at T bar, right? T bar is actually the average. So T bar is equal to the fraction of threes, right? So this is versus the expected value of T bar, right? So this is 1/6, right? So T bar is going to be 1/6. So because this is the form that the Chernoff-Hoeffding bound is in. It looks at averages of random variables instead of sums of random variables. So I need to do a conversion here, right? So I need to divide T. So T bar is equal to T divided by 120, okay? And so then I want to say the probability that this is greater than, then 1/3. Okay, and I see in, okay, so this is, oh, no. I want to say the deviation, I want to know the probability T bar is greater than 1/3, which means I want to say the probability that the difference between T and the expected value, which is 1/6, I wrote this wrong, that the probability, the deviation between T bar and the expected value, which is 1/6, is greater than 1/6, because 1/6 plus 1/6 is 1/3, which would be 40. Okay, so I've done some change of variables to get it into this form, right? The probability that T bar is greater than 1/3, which would correspond with 40, that's upper bounded by the deviation is greater than 1/6. Okay, so I've got an inequality here, but it's pointing in the right direction, so it'll be fine. That is depending on the because I've gone from one-sided to a two-sided bound, and we're just going to always use the two-sided bounds in this course too. Okay, and now I can apply the Chernoff-Hoeffding bound once it's in this form. Now I can plug it into my expression here: 2 times e to the power -2 times 1/6 squared times n, which is 120, divided by, I need an upper bound on my random variables. My TIs, what's delta? What is delta here for TI? It's the difference between the minimum and the maximum value it can take. This was 1. Okay, good. Yeah, this is just the Chernoff form of the Chernoff-Hoeffding bound, if it's binary random variables, right? So this becomes 1 squared. Yeah, okay. Right, so now I can simplify this to, this is equal to 2 times e to the power -20 over 3. If I simplify that correctly, that's 2 times 120 is 240 divided by 36, right? And I guess a 12 factors out. And, okay, so 20 to the over 3, and this is less than 0.0026. So less than 0.3, 3 out of 1,000 times. Less than 3 out of 1,000 times I rolled 120 dice, I get more than 43s. This is the bound I get. Okay, I could calculate it exactly, but this is just an upper bound on the probability. Okay, if we were to apply, I could apply the Shebishev inequality instead. Okay, I need to know the variance of TI, right? So the variance of TI for a binary kind of random variable like this, with probability 1/6 of being true, it turns out it's 5/36. So the variance is 5/36. I can figure that out from the binary random variable, probably 1/6 of being true. So it's now I can apply the Chebyshev. Okay, and so I can again say the probability that t is greater than 40. I'm going to change this again to the two-sided version of the probability of t bar minus expected value of t bar, right, is greater than 1/6. Okay, so this is the same kind of conversion into the pack-bound form that we're going to use in this class, right? And so I can then let's say, or actually I can apply in my notes I did something slightly different, but let's go through with this just so you can see it. Okay, so I can look at what do I need here? I need the variance of t bar. The variance of t bar is going to be, or the variance of t bar divided by n divided by 1/6 squared, right? Okay, let's see if I'm doing this correctly. And this is going to be 5/36 divided by 120 times 1/6 squared. And if I got the right calculations, this is going to give me a bound of 0.42. Okay, so this one only gives me a bound that at most 42% of the time do I have less than 40 of these rolls. Yeah.
Can you explain why the n is in there? Is that just in the Chebyshev equation?
Yeah, so this is the version of so I have the basic version of the Shebishev inequality, right? And here I have for a single random variable, but I can apply this to an average of a set of random variables. And when I have the variance bound of a single xi, I can convert that into the variance of x bar by dividing by n. Okay, and so I directly applied this form. Okay, so when we're having n random variables we're averaging together, you can either apply this version of the Chebyshev or the Chernoff-Hoeffding. Yeah.
Explain again why that's 1/6.
Yeah. Okay, so I'm looking at t is greater than 40. I convert this to t bar. T bar is the average number of threes, which is 1/6. And the expected value again of this is going to be, the expected value of t bar is 1/6. Right. So this one did not have the expected value. I've divided everything by n, and I've subtracted 1/6 from both sides. Okay. And then I put the absolute value. But if I ignore the absolute value, I divide by n to get t bar. I subtracted 1/6. The 40 divided by 120 is 1/3. And then I subtracted 1/6, and I got 1/6 left. Yeah. And then the absolute values, that's the inequality. Okay. Yeah.
The variance that was given for t
yeah, you could calculate. You could look this up on so Wikipedia. I've got a binary random variable that's 1/6 of the time 1. And there's a formula, the variance is 5/36. You can look it up. I will give you this. This is not what we'll test you on in this course. You'll sometimes need to look these things up. Yeah.
Where'd you get the 0.42?
0.42. I did this calculation. Or I didn't actually do it. This was, I derived this slightly differently in the notes I have, and that was the answer. And I'm hoping I did it correct, and it's the same thing. But if you do 5 divided by 36 divided by 120 divided by 1/6 squared, hopefully you'll get that. If not, I may have made a mistake, but I wouldn't get marked off on the quiz, hopefully, if I wrote that. Yeah.
I'm still lost with the one. Is that
The one is from delta. Yeah, so this one here is from delta squared. So this is equal to delta squared. What? Well, I have to figure out from the random variable, right? The random variable varies between 0 and 1, so the maximum deviation is 1. So it's given as part of the formula, right? So part of what you might need to do when you're using this, let me just say a couple more things and we'll wrap up. Part of what you might need to do is you're given a formulation, you need to figure out which bounds can you use, and then you need to convert it into the form of the bound, the left-hand side, and figure out the parameters. Can you figure out delta, uppercase delta? Can you figure out the variance? Can you figure out the expected value? Is it greater than 0, right? And then you can apply these bounds. And you'll check them and see which one they work. Okay, and that's kind of the core thing. There, if you look in the book, there are even a few more examples on some stuff and beyond this in the book. But this will be the end of this sort of section. We'll start linear algebra starting on Thursday. All right, let's see. Questions on Zoom. Okay, how did delta squared? Yeah, so okay, well, let me start. Yeah, I've got a couple of questions on here. Let me start by saying, okay, can you write out the derivation? Oh, the 40, yeah, so I have t is greater than 40. So I know t bar is equal to t divided by n equals t divided by t bar. So I'm going to divide by 120, divide by 120. I'm going to get t bar is greater than 1/3. Okay, now I have the expected value of t bar is equal to 1/6. So now I can subtract minus expected value of t bar minus expected value of t bar. So I'm going to get, that's minus 1/6 minus 1/6. So I have t bar minus expected value of t bar is greater than 1/3 minus 1/6 is equal to 1/6. Okay. And so then, great. And now I can say that the probability of this, right, is less than or equal to the probability of t bar minus expected value of t bar greater than 1/6. This part is true, is the same, but then if I take the absolute value, I get this inequality here. Great. Okay, so how does delta squared become 3 when delta equals 1? Delta squared was equal to 1 in this case. Yeah, okay, and then, yeah, so it wasn't 3. I don't know where that came from. I got a 1, delta was 1, and I got 1 squared here. It's the probability of 1 if this here is the probability of 1 if I roll a 3, and otherwise I get a 0. So I'm counting the number of 3s here. So that's, I think, what the confusion is. Okay, great. Talking about the line 2/20/3. Okay, so this expression here, minus 20/3, is just a derivation of here, the 1/6 squared. This is a 1/36. So what I have here, this part inside of here is minus 2 times 120 divided by 36. And this is equal to 20/3. negative 20 over 3. Right. So that's where that comes from. Okay, great, cool. All right. Great. I'm gonna